Hi, welcome everybody to this code rate session. My name is Jose Escrivá. I'm developer in RAD Studio R&D team, and I would like to introduce you some new features that we have added in RAD Studio Seattle for the Bluetooth low energy stuff. We will focus on the advertising management with the new Advertised Data class and how to turn our devices into beacons with the new beacon device component. This is the roadmap for this session. First of all, we will see a brief explanation on how Bluetooth low energy advertising works, and then I'll explain how we can use the new features in the Bluetooth framework to get data from the advertisement. As an example, we will have a couple of demos which will deal with two actual devices that provide information through their advertising packages. These are the Blue Maestro Tempo sensor and the EM microelectronics beacon with an accelerometer. Next, I'll show you how you can create your custom advertisement using a GAT server in Android. By the way, GAT server support is also a new feature in RAD Studio Seattle. And at the end, we will see how to convert our devices into beacons, simply dropping the beacon device component in our application. Okay, we have a lot of work, so here we go. Let's start by taking a look at how Bluetooth low energy technology works, and in particular the way these devices broadcast advertised data. In Bluetooth LE ecosystem, we will find two well-differentiated roles, considering the way the devices operate. That approach is very similar to the traditional client-server architecture. On one hand, we have the peripheral devices. These devices will be those that act as servers, providing services to which other Bluetooth LE devices can connect to get information. On the other side, we find the central devices. They will be those devices that use the information provided by peripheral devices. The interaction between peripheral and central works as follows. A peripheral indicates its presence by broadcasting advertising packets. These advertising packets generally contains some useful information to identify the peripheral, such as the peripheral's name and or the identifiers of the services that it provides. On the other hand, a central device can scan for these advertising packets and discover nearby peripherals. Once a central has discovered a peripheral in which it's interested, this can request a connection and start to get or interchange data with the peripheral. Once the connection is established, the information interchange is managed by the generic attribute profile on the Bluetooth LE stack, using the attribute protocol. But this is not the purpose of this session. Today we will stop a little earlier, just in the advertising process. Let's study a little the anatomy of Bluetooth LE packets. Bluetooth LE link layer has only one packet format, used for both advertising channel packets and data channel packets. A Bluetooth LE advertising packet has the format described above. The accessed address field shall be always this particular 4 bytes, and the protocol data unit field is divided into 3 fields: a header, a MAC address, and a data subfield. The first 4 bits of the header are the protocol data unit type, that it defines how kind of peripheral is advertising considering its connectable capacity. This table shows the possible values and what they mean. Connectable undirected and non-connectable undirected are the more usual advertised packets that we will find. The first one indicates that a central can request more information from the peripheral that is advertising just by sending a scan request to it. This will not suppose a connection establishment, but the peripheral could send more information to the central through the advertised channel in an advertised scan response packet that has the same format. Non-connectable undirected is the type used when the peripheral does not accept connections, which is typical in beacons, for example. This could be a chronogram of the advertised process. The peripheral broadcasts advertised data packets in a regular manner. If a central device is actively scanning, it could request a scan response to this peripheral and get more data over the advertised channel. But what kind of information we get on the advertised data and scan response data packets? Well, returning to the advertised data, we can see that it contains an up to 31 bytes data field. Yes, that's not a lot of space, but we will have to make do with it. The data field is divided into advertised data sections. Each of the advertised data sections comprise a byte indicating its length, another byte indicating the type of information it contains, and the rest of bytes are the actual information. The different data types that we can find are listed here. The most relevant will be from 2 to 7 that are used to advertise the services that the peripheral provides, 8 and 9 that are used to specify the device name, or the FF, used as a free manufacturer-specific data field where anyone can define his custom payload data. Okay, but if we can interchange data with Bluetooth LE devices through the GET profile, why do we need all this? Well, it depends on what kind of information the device needs to expose. It will be more suitable use the GET profile or the advertised data. Here we have a couple of pros for the use of advertised data. For instance, we can get simpler, cheaper and less power-consuming devices that don't need to implement the full Bluetooth LE stack, since they only use the advertised data to share information. Furthermore, this information can be read by several devices simultaneously, whereas a GET profile connection restricts the data consumption only to the connected device. On the other hand, as cons, the amount of information that can be transmitted is very small, just 31 bytes in the advertised packet and 31 more in the scan response. And this is an unidirectional communication only. Besides this, the information is broadcasted, so any scanning device can read it. Well, how can we catch the advertisement using RAD Studio? Okay, both the T-Bluetooth LE component and the T-Bluetooth LE manager of the framework offer us the OnDiscover LE device event. This event is fired each time an advertisement arrives during the scanning process. In this event, we get an object representing the Bluetooth LE device that generates the advertisement, its RSSI, and a tscan response object. This object is a dictionary of key values pairs, where keys are the different types of advertised data sections, and values are arrays of bytes with the actual data. Since we could have different tscan response objects every time we get an advertisement from a device, for instance, one for the advertised data and another for the scan response, we have implemented a new property for the Bluetooth LE device object, where we are going to gathering all the information that arrives in different advertised events, and that allows us to recover that information in an easier way. Now, the Bluetooth LE device has a new property called Scanned Advertised Data, where all the device advertisement will be collected. This property is an object of the new T-Bluetooth LE Advertised Data, which provides several functions and properties to get the main section information in a convenient and simple way. To illustrate how Advertised Data is managed with our framework, I have prepared a demo that interacts with two actual devices that shares information through the Advertised Data. One device is the Blue Maestro tempo sensor. This device broadcasts the environment temperature, humidity and pressure over the advertised data through the manufacturer-specific data field. In this table, we can see how we have to parse the manufacturer-specific data to get these values. The other device is the EM Microelectronics EMBC02 model that is a beacon device with accelerometer. This device has three operation modes. In moving and fall modes, it broadcasts beacon proximity information when it detects movement or when it is falling. But in sensor mode, this device broadcasts its acceleration through that vendor has called a sensor packet. This packet is just an advertised packet with two advertised sections, one for the device name and another for the manufacturer-specific data, where it provides the acceleration data and some more information, as you can see in the packet diagram. Let's see how it works in the following demo. Okay, here we have an application where we have dropped a Bluetooth LE component and set its enable property to true. This button will start a discovery process with a high timeout for 10 minutes, and this other button will help us to stop the discovery process. We have defined an event handler for the Discover LE device, for the Discover LE device event, and here we are going to display in the memo the entries for the scan response dictionary. Okay, I have launched the application in my Android device. Remember that you need to set the Bluetooth permissions in your project to run on Android. And let's see what we get in the scanning process. As you can see, there are a lot of Bluetooth devices advertising over here. We are working hard with this technology, and this is a little Bluetooth jungle. There are a lot of beacons and other devices, but let's look for the tempo sensor. Okay. Tempo sensor here. Okay. Here we have an advertisement of the tempo sensor. As you can see, it's advertising several sections, but this is which we are interested in, the manufacturer specific data section. Okay. Other interesting section will be the services that it is advertising. Here in the complete list 60 bits UUID, we can see that the device is advertising 1808 service, and we can use this to filter our scan process. Here in the discovery devices method, we can provide an array as a second parameter, indicating that we are only interested in the devices advertising these services. We use this helper class to create a Bluetooth UUID. The service we are interested in is the 1808, and the next time we start the discover process, only the devices that are advertising this service will be found. Let's see it. press the scan button. And as you can see now, the only device that it's reporting deprecation is the tempo sensor, because it's the only device over here that is advertising this service. Okay, and now we will use the scanned advertised data property of the device to get the manufacturer data. So let's see how it works. Okay, press the scan button again, and now you can see how we are getting the values in a regular manner every time that the component detects an advertisement. It's reporting the temperature, the humidity and the pressure in the manufacturer data, and we are passing it in an easy manner. Okay, let's stop it. Okay, we are going the similar thing with the EM microcontroller beacon. I have created also a helper record to get the acceleration value from the manufacturer data. Okay, in the specification of the EM beacon we can see how to get this value. It is represented between the byte 2 and 3 and is in fixed point format. And let's see. Okay, scan, and here we have the events, the advertising events from the beacon. The beacon now is not moving, but if I move the beacon, I am moving the beacon, we get different acceleration values, as you can see. Okay, that's all for the advertising gathering on Bluetooth. Let's see now how we can create our custom advertisement. RAD Studio provides get server support for iOS and Mac since XE7, and now with RAD Studio Seattle we support also get server in Android. It required an Android version 5.0 or Raider, and this is also chipset dependent. Here you can see some compatible chipsets and devices that support this feature. Now, when we create a get server, we also can customize its advertised data. In the same way that we have an advertised data in the Bluetooth LE device, we also have a property in the Bluetooth get server class, the Advertised Data property, that allow us to customize what our get server is advertising. There are some restrictions here because Mac and iOS only allows to customize the services UUIDs and the local name for the get server. All the other fields are ignored for Mac and iOS. On the other hand, Android allows to specify other fields as service data and manufacturer-specific data, but it will always advertise the Bluetooth device name as the get server's local name, regardless what we specify in the local name property of the Advertised Data. Although we can use a workaround, as I will show you in the next demo. Let's see how we can create our custom advertisement in Android and catch it from iOS and Mac. Here I have created a new application with Bluetooth LE component. On the form create event, I'm getting the get server into the fget server field. That is a private field for the form. And at the button press, this button, Advertise, I'm customizing the Advertise data for this get server. A good way of provide a lot of information with little space is to provide an URL. In addition, I use the Google URL shortener service to get very short URL. These are the URLs that I'm going to advertise. What I'm going to do here is to advertise URLs through two different advertise data sections. I'm going to advertise one URL through the service data with this line, binding this URL to 1800 service UUID, and another URL through the manufacturer specific data. What I'm doing here is to encode the string into bytes. That is what we have into all these fields. The manufacturer specific data, it's a byte field, and all the entries in service data have a pair of Bluetooth UUID with the bytes. I'm also adding the service 1800 to the advertised data, so when I will scan, I can filter for this service. Okay. And here, as I have mentioned before, Android always will advertise the Bluetooth adapter name as the GATT server local's name, but as a workaround, we can save the current adapter name and change the adapter name to our custom name, for example McKeith, start advertising, and restore the original adapter name. It's a trick, but it works. Okay, let's launch this application in Android, in a device that supports Bluetooth GATT server. Okay, in the other hand, we have another application that will act as a client. It's a simple application, also with a Bluetooth LE component, a button that starts a discover process and that is filtering only for devices that are advertising the service 1800. And in the Discover LE device event, what I'm going to do is check. Okay, we have two ready buttons. One to choose the advertisement from the service data, and another one to choose the advertisement from the manufacturer data. Then, when we get a Discover LE device event, we are going to check what of the two radio buttons are selected, and depends on what is selected, I get the URL from the data service or from the manufacturer specific data, and then I will load this URL in a web browser component, so the web page will load in the application. Okay, I will launch this application on a Mac. And also I will launch the application on an iOS device, on an iPad. And we will see how the three applications, one server, one GET server, and two GET clients works. Well, we have here the Android application that acts as GET server, and here in my Mac I have the Mac application, and here I'm getting the iPad screen. Okay, let's see if I can see all the devices at the same time. Okay, so if we press scan in this application, this GET client will be listening for advertisement for a device that advertise the 1800 service, only these advertises, and it will parse the information from the service data for the service 1800 and convert it to an URL. This URL will be shown here, and this URL will be loaded in the web browser component here. The same for the iPad. I will change here the radio button because I want that in the iPad we load the second URL. Sorry, here we are going to load the first URL that is advertised via the manufacturer data, and here we are going to load the second URL that is advertised through the service data. Okay, I press scan here, and I press scan in the iPad, and now I press the advertise in the GET server, so it starts to advertise this information. Here we go. I press the advertise button, and as you can see, the application are receiving the URLs, and they are loading the website, one for C++ Builder and one for Delphi Seattle. Also, if I change here the second URL, the other one, remember that this URL is advertised in the service data. If I press again the advertise button, the advertise data will change. We begin a new advertisement, and this application that is waiting for advertisements of service data will change its URL. So let's see. Let's advertise again, and you can see that the web page are changed because the URL that it receives is different. Okay, I think that this is a good way, an interesting way of use the advertised data to advertise a lot of information with a very little space. Let's see now how RAD Studio Seattle allows us to turn our devices into beacon in a very easy manner. A beacon device is just a Bluetooth low energy device acting as peripheral that just advertises specific data that identifies it and its RSSI to allow scanning devices to calculate the distance to it. In RAD Studio R&D we introduced the beacon component, enabling applications to scan and monitor beacons information and calculate the distance to these devices. Now for Seattle, we have developed a new component, the beacon device, that allows us to turn our devices into beacons that advertises custom proximity data. Okay, let's see how the beacon device works in our last demo. Okay, I have here an application with a beacon component that is enabled, and I'm going to respond to the beacon enter, beacon exit, and beacon proximity events, just writing a line in a memo. This application will act as a beacon client. It will detect the beacons over here, the beacons that we introduce here in the monitoring regions. So let's create another application that will allow us to create a beacon. This is to turn our device into a beacon device. Okay, we will use the new beacon device component, put here in the form, and to miss the beacon UUID, for example, 34, okay, whatever you want. We have to put our UUID, and we can put also the minor and the major region, for example 110. Okay. By default, the beacon type is standard. We can create two types of beacons, the standard and the alternative, the alt beacon. This is restricted because in iOS and Mac we only can create standard beacon, that is the iBeacon format, but in Android we can also create alt beacons. Okay, we are going to create a standard beacon, and to get this working, just put a button here, and when I press the button I set the beacon enable to true. Okay, I will put another button to set the beacon off. Okay, this will be on, this will be off. Here we set the enable property of the beacon device to false to stop the beacon advertise. Okay, and we will use the same UUID here that in the beacon client application. We set here in monitored regions this UUID. Okay, setting major and minor to these values, the file values will scan for all the beacons with this UUID, even what major and minor values it has. Okay, I will launch this project, the beacon client, in a iOS device. And the other project where I have put a beacon device component and the other project where I have put a beacon device component I will launch in my Android device. Remember that you have to set the Bluetooth permissions for this works, and this works also in iOS and Mac. You can use the beacon device component also in macOS and iOS. Let's run it. Here is the client application with the memo. And in the Android device we are running the application with the beacon device component. Here it is. Okay, then when I press the on button, the client application detects the beacon and launch the beacon enter event, and if I move the phone I get proximity events. Okay, now the phone is near, now the phone is very close, and also if I press the off button, the beacon will turn off and the proximity away has been launched. Okay, that's all. It's very easy to turn our devices into beacons with the new beacon component for RAD Studio. I think that's all for today, and thank you for joining this code rate session, and now it's time for questions. Goodbye.
Okay, David I here. Let me bring in Diego.
Yep, I got here.
Excellent. Okay. Great presentation by the team. I love looking at beacons and Bluetooth, and I know everybody else loves seeing this. It's probably new for some people who haven't played with Bluetooth devices or beacons so far. So if you have questions, we've got several members of the R&D team online. You can put those in the Q&A log. I don't know, maybe they're still just digesting. Oh, wait, here. There's a question here. Could this beacons be used to make a mesh-like connection? Well, he was, I think it may be a confusion, Bluetooth versus beacons, in the sense that beacons just transmit out information. Bluetooth can send devices, regular Bluetooth, classic devices, can send and receive, right? And so Patricia was asking, are beacons or Bluetooth somehow related to creating a mesh-like, network, a mesh network, MESH? I think because beacons just transmit. They don't receive anything. They don't pass anything along other than the data that's inside of the hardware itself, right?
Right. In this case, the beacons just transmit a small piece of information on never they can receive, just only transmit.
Yep. So if Patricio, if what you're trying to do is create some kind of mesh network, you need devices like network cards or a Bluetooth classic device that might be, Bluetooth built into our computers, for example, can send and receive data. There we have the app tethering technology that can use Bluetooth, and you can then send and receive and create your own kind of mesh network if you want to. But Bluetooth LE, a beacon's just transmit. I guess, are there Bluetooth LE devices that send and receive?
Yes, yes, but they are very limited. I think you can transmit only packets up to 512 bytes of information. For more, you need to cut this into smaller pieces and develop your own small protocol. By default, supported by the hardware, just up to 500 bytes, and this is cut in small 20 bytes packets. If you want more, you need to develop your own protocol.
And that's
it's a bit hard, but Bluetooth LE is not intended to transmit this amount of data. It's just for a small amount, like sensors or medical devices that need to transmit only a few bytes.
Yeah, and the emphasis there is on Bluetooth LE, low energy, and so Bluetooth Classic, which is Bluetooth 3.0, has a longer range. Usually it's built into bigger devices like notebook computers and home automation hubs and things of that kind. So,
right, for things like audio streaming or something like that, it's the Classic is the choice.
Yep. Yeah, no, audio streaming is a great example. Those external speakers or wireless headsets and so on. Yep. If you have other questions for the team on Bluetooth LE, or beacons, you can ask them now, or stay tuned because they're coming back at, let me look at the schedule, at 10 o'clock here in the C++ room on the use of beacons to create beacon fence-based applications. For example, you'll see these appearing in department stores, retail shops, where with an application on your smartphone and being in close proximity to the beacon that's transmitting, it might alert you to a sale on a specific product that's like right in front of you or just a few meters away. So it's really cool technology that's built on top of knowledge about beacons and the beacon runtime. And hence, I guess that's why you talk about the sort of advertising packet. That was where Apple with iBeacons, it was all about a retail application scenario, right, Diego?
Right. The idea behind the e-beacon and beacon in general is very, very simple, but it's very cool. Right now, it's on develop. There are just few applications running, so I think it's a great opportunity for us to expand this kind of application, because it should be a very high demanding. And yeah, the beacon fence session will be very, very, very interesting. The include demos are very, very cool and clear to show how this technology is useful or should be useful right now.
And our beacon support right now is for iBeacon and the alt beacons. Is that right? I think we use the term standard beacon in the object inspector.
Right. The e-beacons and the alt beacon, but not for a platform. For instance, on iOS, we have some limitation due to the iOS framework itself that doesn't support all the alt beacon standard. On Android, for instance, we don't have any problem to supporting all the beacon standard, including the iBeacon and the alt beacon.
Okay. And then I know Google recently talked about another beacon API called Eddystone. Do I remember that correctly?
Mm-hmm. Right. It's correct. Well, yeah, it's basically it's the same that the alt beacon, introducing some very limited variation, but that they develop is another API on top of this standard, adding some any other functionality, but under the hood is the same technology, the beacon that we are using here.
Okay. Then I know we've met with some beacon manufacturers who have their own extensions. I think it was EM Microelectronics had some additional, so it's beacon technology, but they use some of the extra, some extra bytes for things like temperature or impact notification. Mm-hmm. Is that right?
Right. They play with the advertised data in order to transmit this information, like the sensor data, or the gyroscope information, or even cool functionality like the when the beacon is great, there is no advertised data around, but when the beacon is moving or falling, they start to transmit, so our application can detect when this beacon is moving or is falling, and we can read this information, reading its advertised data. It's just the same beacon technology, just playing with the advertised data bytes. Okay.
And I know that I can get things like the signal strength, and we get proximity. I should remember this. Do developers, do they get access to the raw data packet as well if they want to look through the bytes, or do we just give them how we pull out the major, minor, and RSSI?
Mm-hmm. Well, there are the two ways. You can access even the raw data, or we have some helper classes to allow that in an easy way, or access to the classes with properties and with more generated data instead of adding the raw data that is a bit hard to understand and process.
Okay, so yeah, we make it easy. Just get major, minor, get proximity. But again, if you want to explore the runtime library and the classes and methods, you can get at the raw data and do whatever you need, depending on the beacon manufacturer and beacon devices you might be working with. So,
right. There is the Advertise class and other helpers that are perfect for this, to scan or all the data that you are receiving from not only Bluetooth devices, even all the Bluetooth LE devices. For instance, the temperature device that we saw is using the advertised data to transmit the information. It's a Bluetooth LE device, but the information that he's transmitting is on the advertised data. You don't need to connect to the device to get the information. This is a huge advantage because most of the Bluetooth LE devices support just one connection at once. So just one device can connect to this Bluetooth LE device. So using the advertised data allows all the devices around to read simultaneously this information.
Okay, just like the beacons. I mean, 10 people could be walking down the shopping store aisle with their apps, and they can all receive the advertised iBeacons or alt beacon data, as opposed to only connecting with one. Yeah.
Right.
Yep.
Right. There is no limitation in this case. Right.
And what about, now that we have Windows 10, and I know Microsoft's doing Internet of Things work, does that mean eventually T-Beacon runtime would connect to the Microsoft-specific APIs like we do on OS 10, iOS, and Android?
Yes, well, but for that we need to use the WinRT API. Microsoft introduced access to the advertised data in this API.
Okay.
So right now in Seattle we include the support for WinRT API, but you need to use the raw Bluetooth API. There is no helper class at the moment to easily manipulate this kind of information.
Okay. And Jim McKeith is doing a talk at 2 o'clock today on how to integrate and use the WinRT
Great.
Windows 10 platform features. So that's using your own code, but hopefully eventually dropping a T-Beacon on a Windows app running on Windows 10 will have the support eventually, right, for just saying, okay, you're talking with a beacon and here's the data from the advertised packet, I hope.
Yes. We can access to this kind of information on using the WinRT API.
Yep, excellent. Well, okay, Diego, if you have any other words of advice, I know we've talked, and I did a blog based on feedback that you gave us about best practices for working with beacons. One of the things you mentioned was make sure when you get beacons that you calibrate them so that you're getting the right signal strength and proximity information. Is that right? Do you have advice for developers who are going to start developing beacon apps about best practices they should look at when they're going to start doing development and work with these little beacon devices?
Right. The most important is that you mentioned the calibration of the beacon, because if a beacon is not calibrated, it is transmitting a wrong information. So it's not only about this beacon is not won't work very well. So they are going to get wrong to our application. So I recommend to all the people, if you want a complete information about the beacons, to see the beacon fence session, because there are specific information in this next session about the beacon, the practice, and so on. Because as the beacon fence is strongly related with beacons, we include some very useful information in this session.